I don't want to sound glib and say I don't care, because I do care. I want to be able to make measurements that will allow us to constrain it. But the universe doesn't care what we think it should be. I don't think I have any say in what the universe should be.
Wendy, it's great to see you. I looked, it's been 13 or 14 years, frightening. But this has been the most exciting time in precision cosmology. I've followed what you've been doing, your accomplishments. Give me a sense of what the last decade or so has been like, chasing the Hubble Constant, the Giant Magellan Telescope. Now, congratulations, university professor at the University of Chicago. How's it been?
Well, it's really nice to see you again too, Robert. It's been quite a while and an exciting intervening time. The After the key project where we did this big program with Hubble to measure the Hubble constant, I thought I was done measuring the Hubble constant, but we have developed new techniques and new facilities have become available that have allowed us to make much more accurate measurements. And so now we have found ourselves in a little bit of a new debate, tension, crisis, some people have called it. As the measurements have gotten sharper and sharper, things have tended to disagree again, as they did over 20 years ago. And yes, in the intervening time, I became the director of the Carnegie Observatories. I may have been that when I spoke to you last, and took the lead in a giant telescope project, one of the 3 large telescope projects in the world, called the Giant Magellan Telescope. And that, in fact, just cast the sixth of 7 mirrors last week. So that's a pretty exciting milestone. And yes, I moved from Pasadena, California, my home for 30 years, to the University of Chicago, where I now teach and have gone back to full-time research. So it's been an exciting period, lots of changes, lots of new and different kinds of things.
We have some parallels. I lived in Pasadena for 40 years and moved. My move was shorter. I moved to Santa Monica, but a little bit New York as well.
Better weather.
If I had to pick out the greatest scientific discovery in terms of transforming humanity's understanding of all reality and humanity's place in all reality in the cosmos, it would be the discovery that there are multiple galaxies, because forever everybody thought of just one galaxy, and the expansion of the universe. The two things came together with Edwin Hubble. So let's understand how did that happen? Let's give the background of how was the expansion of the universe discovered, multiple galaxies discovered, and from there, then we can go into the Hubble constant.
Yeah. By the way, I would agree with you. I think in terms of changing humanity's perspective on the world, the universe that we live in, those are 2 major discoveries that really changed our perception of the universe. And if we step back, there was before Edwin Hubble, we did not know of the existence of other galaxies beyond our own Milky Way galaxy. And there was a question about whether or not there were regions that had spiral shapes. They were called nebulae. Nebula is the Latin word meaning fuzzy. And those had been known for quite some time. And there was speculation that they might be regions in the Milky Way where gas and dust were collapsing to form new stars. So that was one possibility. There were new stars in the Milky Way. And there were others who thought maybe they were island universes, as they referred to them then, like the Milky Way, but at much farther distances. And there was no way to distinguish in between those 2 possibilities, because we didn't know how far away they were. And so Edwin Hubble, when he came to Pasadena to use the telescopes at Mount Wilson, was interested in this question of the nature of these spiral nebulae. And so he used first the 60-inch, then the 100-inch telescope at Mount Wilson to take large photographic plates. That was the detector at the time. And he came and observed the sky with these photographic plates over and over and over with these nebulae in his field of view. And what he found was that there were pinpoints of light within these spiral nebulae that were changing their brightness over time. And they turned out to have a very characteristic pattern. It was there was a type of star called a Cepheid variable that had been known since the 1700s. They rise in their luminosity very rapidly, and then they fade very slowly. And he was able to say, I have found Cepheids in, for example, one of them was the Andromeda Nebula, which you can actually see in a dark site with the naked eye. And based on those observations, he was able to establish without any doubt at that point that these objects were far away, not contained in the Milky Way. The universe was much larger than we had thought if the universe was defined by the extent of our own Milky Way galaxy.
So how did he do that? What was the technology? Because that the way you can come to that conclusion seems remarkable. You see a variable light in a galaxy, and then you can determine the absolute distance, and that will characterize all the other things that we'll be talking about. So let's understand how he did it, because that was the radical methodological breakthrough.
Yeah. And so if you're trying to determine the distance to another object, to a star or to a galaxy, you have to know how bright the object that you're observing actually is. So the wattage, as it were, the power, the absolute luminosity that's being emitted. And so today, in a modern sense, we can use parallax, a geometric measurement that comes, where we can do triangulate, use the fact that the Earth is going around the sun and observe the star at different times in the Earth's orbit to literally use high school geometry, parallax, and determine the distance. Astronomers have had to be creative over the years in getting an absolute calibration, because stars are so far away that the parallax motion is very, very small. And so
And you have to do it against the background of even further stars that you have to assume almost that they're constant, and they're not. It's just a huge difference. Effectively, they're constant.
That's correct. And well, effectively, you can't measure them. It's so small that you really can't measure them. And so that was one of the difficulties when Hubble first measured the expansion rate or measured distances. The absolute calibration was very uncertain. So his value is about 7 times off, a factor of 7 from what we measure today. And a lot of that had to do with the calibration that he used. It just, he didn't have parallaxes available to him. But in any case, he was able to say, these are Cepheid variables. We can compare them with other techniques. Cepheids are in clusters. We can measure the distances, say, to those clusters using different techniques. In fact, he didn't even have clusters available at that time. But then he was able to determine, one, these galaxies are at large distances, but then he also used velocities of these galaxies that had been measured by Vesto Slipher. And he was able to show that there was a correlation between the velocity of a galaxy and its distance. And that is what we refer to today. The slope of that of that relationship is the Hubble constant.
Right. So the relationship is between the distance from us and the speed, and that ratio. That's high school algebra.
It's very simple in principle. It's extremely difficult in practice.
Right. So yeah. we're gonna talk about that, but I want to understand, although, why that is important. What is it about the Hubble constant? I mean, there are innumerable constants in physics. 26 parameters in the free parameters in the standard model. A lot of constants in physics, but why is the Hubble constant so critical to cosmology?
So again, the context of these discoveries of Edwin Hubble, they came very shortly after the development of the general theory of relativity by Albert Einstein. And general relativity is a theory of gravity. And the implication of Hubble's results, so he measured this correlation between the velocity and the distance to a galaxy. So what we're seeing is that galaxies that are farther away are moving away from us at faster speeds than those nearby. And so in a sense, we could run a movie in reverse or integrate Einstein's equation that govern the dynamics of the universe. And what it implies, if the universe has been expanding, we see it expanding today, would have been expanding in the past, and that would have meant that the galaxies we see today would have been closer and closer together the farther back in distance or further back in time that we go. And what that led to, combined with Einstein's general theory of relativity, is this Big Bang model for the expansion of the universe. So why is the Hubble constant important? It essentially is the most essential parameter that governs the dynamics, the evolution of the universe. It sets the age of the universe, because if you can integrate backwards to when this Big Bang occurred, then you know how old the universe is. It sets the size scale for the universe. And if we can measure it very accurately today, why it's become more important again is we can compare with our cosmological model for the evolution of the universe and test to see whether the model is correct or not by making measurements very early in the universe and extrapolating to today. So it's a fundamental parameter that really sets the size, the age scale, and governs the dynamics of our universe.
It's of historical interest, but very substantive as well, that Einstein thought at his time, he didn't know about the expansion of the universe and assumed a steady state model, which may have been the logical thing to assume. But his equations led to an expansion. So he put in the so-called cosmological constant, because he had to have a fudge factor to keep everything together. And then he later said that was the biggest blunder of his life. His blunder was thinking that his original equation was wrong. That was his blunder.
That's right. And because his equations were actually screaming that the universe had to either be expanding or contracting.
Right. Yeah. We all should have those worst blunders in life.
Yes.
So at that point, in terms of measuring it, because you're measuring the variables techniques, and we're going to get into that, at different times in different locations in space, which are going backwards in time. So it is possible that if you're accurate enough and you can segment the periods of time, you can test whether it's constant or not, or maybe it's changing. I mean,
Exactly.
that's a fundamental new physics, maybe, that it's not it's different people measuring it in slightly different times.
Yes. And in fact, we do know that the universe changes the rate at which it's expanding over time. And that's actually what's led to this idea of dark energy, and that there may be a cosmological constant, which Einstein had called his biggest blunder. So we call this the Hubble constant, which tells you it's constant at the current time. If we look in different regions in the sky, we measure the same value, or we hope we do. People get slightly different answers because of measurement error. But as we look back in time, at larger and larger distances, greater and greater redshifts, the expansion rate does change with time, in fact.
All right, let's spend a little time digging into how this actually works. And I think one place to start quickly is the redshift, because that gives you a sense of time and of the age of what you're looking at. So briefly describe that.
So, a familiar example that we use. So the redshift describes the universe is expanding. It's and the way that we characterize that expansion is by redshift. So how many factors the universe has changed its size over time. And so in a simple example, well, let me say first, the velocity versus distance plot of Edwin Hubble's holds in the nearby universe. We can measure the velocity and measure the distance. And you can think of it, the redshift, as analogous to the Doppler effect for sound. We know that the pitch of an ambulance siren or a fire truck siren changes when it's approaching or it's receding from us. And so we can measure the shift of spectral lines, compare them to the positions of those wavelengths of light in a laboratory. And that shift is a measure of the expansion, or the redshift.
Because as the universe expands, the waves get pulled apart.
That's right. And so that's actually what's happening. Because the universe is expanding, the wavelength of light is being stretched. So it's not quite a Doppler effect. Because of the expansion of space itself,
Right.
light is the wavelength of light is being stretched, so it's redshifted. And so in Hubble's discovery, there are very few galaxies that are approaching us. There are maybe a handful of galaxies. Andromeda is one of them. It's approaching us, but the vast majority of galaxies are actually expanding away from us. We say that they are redshifted. Their light is shifted to the red.
Yeah.
And so we can use the redshift as a measure of essentially the distance to a galaxy.
And what's the scale of redshifts from 1 to 10? What is how do you measure what's the scale?
Well, today, so we are at 0 redshift today. The farthest back that we can see is a redshift of 1100. And that's the remnant radiation from the Big Bang.
Right.
When it is able to, the photons from the Big Bang can reach us because they stop scattering off of the hot plasma from the Big Bang. That occurs, that's about 380,000 years after the Big Bang. That's a redshift of 1100.
The microwave radio background is really remarkable. We'll get into that. But in terms of an actual galaxy, what's the largest redshift for an actual galaxy?
People are measuring redshifts now 6, 7, 8. So we go out to those redshifts.
And that'll go back to a billion years after the Big Bang. So, roughly 13 billion years ago from now, you can get that redshift variation. So redshift is the first kind of methodological foundation. The second is an important term. We've described it, but I'd like to go into more detail, is the concept of standard candle. So if you know, as you said, the wattage of something in an absolute sense, and that's standard, it's like a candle at standard, then however far away from it, if you know how bright it is, if you're right up close, you can make a prediction of the distance based upon the visibility or the brightness of it.
That's right. And so it's much easier to measure the relative distances to objects. So you can say this object is dimmer, therefore it's farther away, if you know the wattage.
Right.
And so there is an inverse square law for light, just as there is an inverse square law for gravity. And so if you know the wattage and you can measure the luminosity of your star and see how relatively bright it is, then, so for example, with the Cepheid variables, if you say that the Cepheids that Edwin Hubble used and we use today have a relationship between how bright they are and how fast their atmospheres are varying. There's a relationship between the period and the luminosity of a Cepheid. This was discovered by Henrietta Leavitt just over 100 years ago, working at the Harvard College Observatory. And so if we can measure the wattage of a Cepheid of a given period in our galaxy, calibrate that, and then measure a Cepheid in another galaxy at the same period, and we see how what its apparent luminosity is, then just by the inverse square law of light, we can determine the distance to the galaxy because of this 1 over distance squared dependence of luminosity with distance.
Now with the Cepheid, how far can you go? Because I would think there's a limitation in terms of where the brightness could be measurable at all. So how far back can you go with the Cepheids?
So with the Cepheids, we can measure reliably, I would say, out to about 30 million parsecs, which translates into about 100 million light years.
Yeah, that's really short.
That's really short, which gives you some sense of why this is a challenge to measure the Hubble constant.
Right.
And so we can't simply measure the Hubble constant using Cepheids alone. We have to tie into other methods where the objects are brighter. So we use generally supernovae, a particular type.
So let's talk about that. It's funny in cosmology, 100 million light years is really short. Just like in today's world, $100 billion in the federal government is really small.
Yeah, what was unimaginable before. That's right.
So let's now go into the other kinds of standard candles. We understand the Cepheids, how they work, luminosity versus period, and the limitation they have in terms of distance and time. So what are some of the others? I know the supernova 1A, how does that work?
So the supernovae are the explosions that occur at the end of a star's lifetime. Cepheids are pretty young stars. They're in the early phases of evolution. But supernovae are objects that we believe are in a system, a binary star system. And they have cores that are very, very dense. And either two of these stars, known as white dwarfs, collide and create an explosion, or you have a single white dwarf with a companion star that's putting mass on this white dwarf. And when you exceed a certain mass, the star explodes as a supernova. And that brightness can exceed the luminosity of an entire galaxy for a brief period of time. So we can measure those out to billions of light years away.
Okay.
And so that is, at the moment, the most accurate means that we have of going out into the distant universe.
So again, how do you know that each supernova has a standard absolute brightness? What independent variable? Because maybe they're all different kinds, and earlier they were exploding with less or more mass. So
Yeah,
how do you know that?
and we do worry about that. And in fact, they're not perfect standard candles in the sense that they all have the same luminosity. The rate at which they fade in their luminosity is a function of their luminosity. And so it's not unlike the Cepheids. Brighter Cepheids have longer periods, and brighter supernovae decay more slowly. And so we have to calibrate that.
I'm always looking for the method of how you do the calibration. I love the Cepheids because with some of them, you can do the parallax. And if you do parallax, you know for 100% sure that you got it, because this is, as you said, high school geometry. You see the variation, you have the angles, and you know exactly what the hypotenuse is or whatever. And that's wonderful. And so everything that can be tied to that. But once you go out beyond that capability, I always feel a little nervous that there's some leaps of faith in there, that you're not really getting an absolute standardization to make the claim that the supernova is a standard candle.
Yeah, and those are the kinds of things that we really do have to worry about. And we're now at a time in cosmology, and actually the bar has been set very high by the measurements, very precise measurements that are made of the fluctuations in the Big Bang background radiation. But these are the kinds of things. These aren't light bulbs where we know the wattage perfectly. We have to find a way of determining how secure is that luminosity that we're measuring. And so, for example, with the Cepheids, just to take an example, these stars are going through their stellar evolutionary tracks, and as newer stars are born, they're born at a material that has a higher chemical abundance than the earlier generations of those Cepheids. And so this is something that I've been worried about for over 30 years. We tried to devise a test to determine, is the luminosity of a Cepheid dependent on its metal abundance?
Oh, yeah, sure.
By the way, astronomers refer to metals as anything heavier than hydrogen and helium, just so you know. So carbon, nitrogen, oxygen, all those good things are metals to astronomers. But so we can do tests, we can calibrate how large the effect is, we can measure that, but there's always some associated uncertainty with that kind of measurement. We have to worry about dust in the intervening region between the Cepheid and us, or the supernova and us. And so the way we get around that is to make observations at many different wavelengths or many different frequencies, because dust has a characteristic behavior with wavelength. And so there are ways to get around this. This is what I've spent a great deal of my career working on, is how do we correct for these types of things? But there'll always be some measurement, first of all, measurement uncertainty, and then there'll be potentially intrinsic properties of these objects themselves that might be contributing some sort of systematic effect. And
let's look at some other standard candles. You've been working recently on the tip of the red giant branch, and that's one I was not as familiar as with Cepheids and supernovas. So what is that? How does that work? How significant is it?
Yeah, I think it's quite significant. I think for the future, it's going to be even more significant because of all the distance indicators we talked about so far. It's the most standard candle-like,
Hmm.
the fewest corrections that have to be made. So in this case, these are stars that are low mass, unlike the Cepheids. They're older population. And what's happened is they have a very dense core again. There's a core made of helium. It's a degenerate core. And when these stars undergo something called the helium flash, when you have enough mass and the temperature has become high enough to burn helium, the star rearranges its structure and then disappears. It never gets any brighter than the core helium flash luminosity. And so it's the physics of the evolution is very well understood. And because this occurs at almost constant mass, the luminosity is it's the same. We don't have to make corrections we don't have to have a Cepheid period luminosity relation or a supernova decline rate relation.
And the reason the mass is the same is that you need that mass to trigger that event.
That's right. They reach that mass, and the temperature is about 100 million degrees at that point, at that given mass, and then that's when the helium flash.
It's like an atomic bomb where you can have uranium-235 and two pieces, and they're completely inert, and you put them together because you exceed the critical mass.
But the fortunate thing is it doesn't blow up like a supernova. It actually just rearranges its internal structure and then becomes a lower luminosity star. But what happens is when we go out and look for these stars in nearby galaxies, we find stars of all luminosities until we reach that core helium flash luminosity. And then there are no stars above that.
Oh, okay.
And so it's a very clean measurement, measuring this tip of the red giant branch.
How far out can you go with that?
So we can go as far out as the Cepheids with the Hubble Space Telescope and with the James Webb Space Telescope, and that will be launched in October of this year is the launch date. We'll be able to go.
We hope.
We hope. Yes, we hope.
It's been a long travail, but yes, go ahead. Sorry.
We hope. And then we'll be able to go out to a volume 8 times larger. So we'll be able to observe many more galaxies. And we're looking forward to that.
Right.
But the nice thing is that we can find them in the halos of galaxies. The Cepheids are young, so they're confined to the disks of galaxies where there's dust and gas and blending of stars because the bright background of the galaxy disk. But in the halo, it's very diffuse. There's no dust. And so we can make these measurements very, very accurately. So this is not as far along as Cepheids we've known about for over 100 years now. We've been using them to measure distances. And but I mentioned that Harlow Shapley, when he was first talking about the extent of the Milky Way, this early debate about whether there were island universes, he used these giant stars. He got it wrong, as Hubble did. His distance scale was off, but we've known about these stars as potential distance indicators for a long time. But it's only the last 20 years and now the last 6 or 7 that we've really put effort into developing them to measure the Hubble constant.
You're their champion.
Yeah.
So we have these 3, Cepheid, Supernovae, and tip of the red giant branch. What other methods? Now, the CMB, the cosmic microwave background, is a different kind of test of the Hubble constant. So how does that work?
So the interesting thing about the background radiation is that there are small differences in temperature. Look across the sky, the background radiation is not perfectly smooth. It's almost perfectly smooth. It's 0.001% fluctuations in the temperature.
Right.
And it's a phenomenally precise measurement. And now also they can measure the polarization of that radiation. And you can plot essentially just the power spectrum of these fluctuations, and encoded in the fluctuations, which actually are due to quantum fluctuations in the early universe, right, that are the seeds that grow into the galaxies and large-scale structure that we see today. And we see an imprint, the fluctuations in temperature, on this surface of last scattering that I mentioned. So in the first 380,000 years after the Big Bang, this hot plasma is full of electrons and protons, too hot for the electrons and protons to combine. And the photons keep getting scattered by the electrons. until the expansion has proceeded far enough that it's cool enough for the electrons and protons to combine, and then the photons can stream away, and we can measure them today. And you can measure this fluctuation spectrum extremely accurately and fit them to a cosmological model. So what has become, since we last talked, the standard cosmological model has the visible matter that we see, that we're made out of, the dark matter whose existence we infer from the motions of galaxies and other techniques, this dark energy, the cosmological constant of Albert Einstein's, and you can use that model then to infer what the expansion rate today would be, and you get a value of the Hubble constant. So we haven't mentioned yet. So the value of the Hubble constant that we get if we use Cepheids is 73 or 74 kilometers per second per megaparsec. That's almost identical to the value that we got as part of the key project in 2001, when we first used Hubble to resolve, at that time, a factor of 2 debate. What we're getting from the red giants is just under 70. It's about 69.5 kilometers per second per megaparsec. And the microwave background observations are giving 67.4. Now, when you and I last talked, the Hubble constant had been uncertain at a factor of 2. We didn't know if it was a 50 or 100.
Right.
We got 72 at the time with an uncertainty of 10%. That's why, I didn't think I'd ever want to work on the Hubble constant again, because we'd solved this major discrepancy. But now there's a new discrepancy. And given the error bars between the Cepheids and the microwave background, that could be significant if the Cepheids turn out to be correct, and there's not some systematic error that we don't yet understand.
When you say the error bars are do they overlap or
no,
gap? There's a gap in the error bars.
There's a gap in the error bars.
Yeah, that's significant, because that's the confidence level is very high within those error bars, and if they're not overlapping, that makes you nervous. So let's really get into the tension, because that's dominating the field. That's what you're focused on, and many others. I'd like to sort of begin that by saying, what's the significance of the tension? What are the potential options that makes this tension so important?
So given this, what we now call standard cosmological model that includes all the constituents in the universe that we know of, the matter and energy, we then can, as I said, infer, we can predict what the expansion rate would be today. When we measure it directly, as we have with Cepheids and supernovae, or now tip of the red giant branch and supernovae, that's a test of the cosmological model. And it's possible that both the high and the low values are correct, and that something has changed from the surface of last scattering 380,000 years ago to the present day. And so our standard model has only been with us about 20 or so years. Maybe there's some fundamental piece of physics that we don't know of yet. And this would be a way to determine whether there's some fundamental physics missing from the standard model.
Because
so that's what has people really interested. It could be signaling new physics.
And let's just see what that would mean. And the reason is what you're getting with the cosmic microwave background is a picture, a static picture of the way it was, what that constant was when it's there, which was right after the Big Bang, 380,000 years. Everything else you do with the Cepheids, supernovae, tip of the red giant branch, all of those have different time frames that you're working in. They're different time frames. So if they differ, they can differ because of a systematic error, and they really should be the same, or that they're really representing the reality of what is happening at different time periods. And then you have to explain that, and that's all.
That's right.
So how?
That's right. And I should say the standard model does a remarkable job of explaining many things. It's consistent with 3 flavors of neutrino, with measurements of the amount of dark matter in the universe, other independent measurements from supernovae of the amount of dark energy. the fluctuations in the matter density. There are now a whole host of observations that it fits very well. So the question now is, okay, given this superb fit, and if you see I'm realizing my internet connection is unstable. Did I lose you?
It's okay.
Okay, good. The fit to the microwave background spectrum, the fluctuations, is remarkably good. and the challenge now is if you try and change something and you say the Hubble constant actually is higher, the way some measurements locally are saying, it has an effect on all of the other parameters that it fits so well. And so the sort of constraints have become tighter and tighter and tighter, so that now if you want to explain this discrepancy, you have to say that this happened, the early universe physics, so early that we don't detect its effects later on in any other way. And people have speculated that perhaps there is some sort of scalar field not too dissimilar to what caused the inflation period in the universe that causes the expansion rate to be higher, and then it turns off right at the point where all these other things are being measured after recombination.
Very convenient.
So right now, it's very convenient, and so there's no fundamental reason why you would have it, which doesn't mean we won't find one ultimately, but there's no satisfying answer right now for what it could be if it's a true physical effect.
How many different?
And then we now have a new tension. Sorry.
Yeah, I was saying, how many different time periods can you isolate in your studies between where we are today and what the CMB would show? Are there different time segments?
Yeah, so they're now possible to measure fluctuations in the matter density, for example, so-called baryon acoustic oscillations, which give you a nice measure, again, of the expansion rate history over time. Supernovae allow you to measure as a function of redshift, but not quite as far. And most of the measurements that we're comparing are actually fairly local, even including the supernovae, relative to the distant microwave background observations.
Yeah, that's always a challenge, because you know, in this, as you said, the first 100 million light years, you have a lot of data, but that's a very small fraction. That's you know, 1,000th of the total period. So you know, there are concerns along that. What do you see as the trajectory, the next steps? You know, where are you today?
I think the next steps are really clear. First of all, there's a satellite called Gaia. It's a European satellite that's measuring very precise parallaxes to the nearest stars in the Milky Way, and also the nearby Magellanic Clouds. And that hasn't yet achieved the kind of accuracies that we need, the 1 to 2% that we're talking about, that would help resolve this kind of Hubble tension. But that will happen in the next few years. And that will lock in the wattage of the Cepheids, of the red giant branch stars, and other techniques that we're actually working on at the moment too. The other is James Webb, which I mentioned, which will allow us to go to larger volumes to measure more tip of the red giant branch stars. I should say that supernovae themselves are rare. And so a supernova that we can actually measure a distance to the galaxy in which it resides with Hubble happens only every 1 to 2 years. So on average, 1.5 years before we get another galaxy. So the sample size now is, there are 20 or so galaxies we can measure. We might be able to extend that to 40. But with the James Webb, we'll be able to significantly increase that to order of 100.
A good question is what is the sample size for each of the techniques? For the CMB, we know that in essence it's one data point, or I mean, a lot of information.
One universe, but a lot of individual points, a lot of frequencies,
right,
a lot of
points, but it's sort of one thing. And with the Cepheids, with the supernovae, roughly what's the order of magnitude of the data points that you have or will have?
Yeah, so we start with the absolute, call them anchors, for the geometric measurements. The number is about 3. That's a small number.
Yeah.
parallaxes or other kinds of geometric techniques, and
Right.
we could go into those. There's something called detached eclipsing binaries where you can measure rotations and so radial velocities and photometric light curves, and another technique using masers. So there are three objects that Milky Way parallaxes, a galaxy with a maser distance, and a galaxy with a detached eclipsing binary distance. Then you step out and you calibrate in nearby galaxies, either with Cepheids or tip of the red giant branch. And there's of order 20. And then you step out to the supernovae and the samples go from 100 to 1,000.
Okay.
So we have lots of supernovae. Statistically, supernovae are not going to be the problem, and we don't see many differences there. The anchors, there are choices as to how you, what field in, for example, the galaxies you're looking at are doing the calibration. And then there's the middle zone where we are pushing out to distances. This is what one of my worries now. Have we tried to push Hubble too far? And that, I think, is an area that we need to explore in more detail, because we do see this difference between tip of the red giant branch and Cepheids. And unlike the case of the universe, where it could be very interesting physics that's missing from the standard model, there's only one distance to the galaxies that we're measuring, right? They're at one distance. So it's already telling us there's something we don't understand in one or both of the methods. And until we understand those differences, I think, in my view, it's premature to claim that there's fundamental physics missing. I mean,
that's a methodological kind of problem as opposed to a new physics issue.
Right.
I'm going to do something very unfair, and then I'm going to ask you to make a prediction of where you think this will come out. If we're sitting here, and I plan to, 30 years from today, and we're sitting here, we may have, dye our hair or something, but we'll be sitting here 30 years. And looking back, what would you like to say then, and your prediction now?
So if I were looking back at 30 years, I would like to say that we have measured this. So I think if we confirm the standard model, that is a really important result. If there's new physics, that's a really exciting result. And I don't want to sound glib and say I don't care, because I do care. I want to be able to make measurements that will allow us to constrain it. But the universe doesn't care what we think it should be. I don't think I have any say in what the universe should be. And I think this remains a really interesting question, because I've worked on Cepheids for a long time. They're indicating something different. Now I'm working on the red giant branch. It maybe is not indicating something different. And so I do worry there may be systematics in the Cepheids, but there may be systematics in the tip of the red giant branch. And as we narrow these down, we'll find something interesting. I don't know the answer.
Yeah,
I don't think anybody does.
Right. But I think most people would say that you don't really expect anything as dramatic as what was discovered in the very late part of the last century, 1998, the accelerating expansion of the universe, because that was exactly the opposite of what was expected. It was shocking, and that demanded new physics with dark energy and everything else. So can you say that the expectation is not something at that order of magnitude?
Yeah, I agree with that. And I think more to add to what you said, there were many pieces of the puzzle that didn't fit at the end of the 1990s. And we didn't, so there was a discrepancy in the age of the oldest stars and the Hubble constant. We were measuring the expansion age. In modeling the distribution of galaxies, if there wasn't enough matter plus energy in the universe, you couldn't explain your large scale simulations for many reasons. Good reasons. The density of the universe was thought to be near a critical density, but astronomers couldn't find the rest of that matter to make it a critical density in matter. And so dark energy solved many, many problems simultaneously. This one is different in the sense that the only problem is this difference between the Cepheids and the cosmic microwave background. The precision in the microwave background measurements is very high, which I think is a good thing. It set the bar very high, and those of us making local measurements really have to reach that bar. And so, so whatever physics is discovered is going to have to also be consistent with everything else we know, but it does at the moment at least seem pretty contrived. We'll see.
Good,
We'll
that's
see.
great. Tell me a little bit about the Giant Magellan Telescope. I've been rooting for it ever since it was first speculated upon, and exciting to see that 6 mirrors have been cast. When do you expect to see first light?
So first light now is for 4 of the mirrors will happen, we hope, by the end of this decade. And then the other 3 mirrors would come online in the first few years of the next decade. So it's been a long process. This is, again, you don't buy these off the shelf. These mirrors are phenomenal mirrors. Each one of the mirrors is 8.4 meters in diameter, so 27 feet in diameter. The
And
whole
by
telescope, yeah, is a
so that's
25
like
meter.
320 inches for one of them, and the original what from decades was the largest telescope in the world, the Hale, is 200 inches. So this is significant. Each one of them are significantly larger than the whole Hale. So it's a remarkable.
It's an 80 feet in diameter mirror. So it'll be located in the Andes Mountains in Chile. And
are you moving there?
no, but I sure hope to use it.
Okay.
That's no. And it's a telescope that I think 2 really exciting things off the bat will be to study planets that have masses similar to the Earth, to actually look at their atmospheres and to see if they have potential signs of life. So carbon dioxide, water, methane, ozone, and to actually be able to measure velocities of the stars that the planets are orbiting, and allow you to determine the masses. And right now it's very difficult to find Earth mass planets. Jupiters and Saturns and Neptunes and so on are easier because they're more massive. But it's really going to usher in an era where we will be able to ask questions about the nature of Earth mass planets elsewhere in the nearby solar neighborhood, which is pretty amazing.
How about cosmological questions?
Cosmological questions. So in terms of studying dark energy, dark energy is a function of redshift, again, to look at its evolution. It will be important for studying dark matter. It will still, I'm hoping we will have solved this Hubble tension before then, but in terms of providing more accurate measurements, we'll be able to go to larger distances with tip of the red giant branch, for example, or Cepheids. And studying black holes, we'll be able to see black holes essentially at all distances in the universe with this telescope. We will also be able to see what we call the first light in the universe, which will be very synergistic with the James Webb Space Telescope. So I described this period 380,000 years after the Big Bang, when the first photons could get out. And the first galaxies started to form after that, as the universe was cooling and matter began to clump due to gravity. We had the first galaxies forming. And with Hubble, we can see sort of faint smudges as we look back in time, but we don't get a lot of information. And with these new giant telescopes, we will have 10 times the resolution of the Hubble Space Telescope and actually witness when these galaxies were first forming. So that, I think, is going to be another really exciting thing that we can do. But every time we've had a jump in technology, bigger and bigger telescopes, and without exception, we have made new discoveries with newer and bigger telescopes. So I think the discoveries that we can't even anticipate are maybe even more likely to be the most exciting that we make.
So I'm going to ask you for 2 dates. One is about a decade from now, and after you get first results from Magellan. And second is what I've said, 30 years from now, I want to look back on Hubble and see what has happened, and to see our understanding of the universe. Do I have the 2 dates?
You absolutely do. I commit to them now. And I'd be very interested to see where we are.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.